Welcome to Introduction to Quantum Field Theory 19. We'll be talking about Dirac equation solutions. I should have written this in before the video started. But in the last video, we talked a little bit about solutions, namely capital Psi equals the F times lowercase psi. This is, of course, the spacetime structure, and this is the spinor structure. So in this video, we will discuss why F exists as a part of the solution, and then how we can figure out the spinor structure here. First, let's discuss a neat way to rewrite the Dirac equation. So rewriting the Dirac equation. The first step is to define something called the Dirac operator, which is this curly D, and it's just I gamma mu partial mu minus. So this is the Dirac operator. Dirac operator. And if you remember before, the Dirac equation is just this I gamma mu delta or partial mu and then m. So if you were to subtract this over here, then you just get this operator times psi. So this implies, there we go, a little better, implies that the Dirac equation can be rewritten as this. The real reason that we want to rewrite the Dirac equation is so that we can consider complex conjugates of the Dirac operator. Now, we can consider complex conjugation of the Dirac operator. So not the spinor. I said Dirac. I said spinor before, but I meant to say Dirac operator. And we're going to have that 0 is equal to the Dirac operator with the complex conjugate times the Dirac operator times C here. And notice that if we were to multiply this on the left, or on 0 by this Dirac operator, it also is 0, so this whole thing is still equal to 0. And if we expand this outward, then we end up getting a negative sign in front of the entire thing here, plus m, and then an I gamma, and then we're just going to say that, or we have to say, because they're interacting via multiplication, that these indices are different. And then, or minus m, and then times the Dirac spinor. So if we expand this out here, we're going to have a negative sign out front, then minus, we're going to have I squared gamma mu gamma nu partial mu and then plus m I gamma mu partial mu, or hang on, sorry, news, then minus I gamma mu partial mu minus m squared, all of this times the Dirac spinor. So this is from this times this is from this times this, and this is from this times this, and then m squared is from this times this. So let's simplify. We can first distribute this negative sign, and not only can we distribute this negative sign, but notice how this isn't, these two terms are not interacting with any other terms that have different indices. They are just being summed together. So because they're not directly interacting via multiplication, we can actually relabel this. So the best way to do this is just to copy, paste, and then this negative sign will cancel with this I squared. So we just get that this is positive here. And then this becomes mu, mu, and this becomes minus. And this becomes plus. We can write a better plus than that. I guess not, maybe not. No good pluses on my end today. Okay, so we can rewrite it like this. Well, this just goes to 0. So we get gamma mu, gamma nu, partial mu, partial nu, plus m squared, capital P. So recall that these partials here, these partial components, those are like scalars. So I could reorder this and it doesn't mean anything. But remember, these gammas are the Clifford algebra generators. So these are gamma matrices, not scalars. So they don't, while these commute right here, these don't commute, they anti-commute. So we're going to take advantage of a property here. If I have AB, then AB is the same thing as AB half plus AB half, and then plus BA over 2, and then minus BA over 2. So we're going to use this property in the next step, which you can see clearly this is the same. These add up to AB, and then these cancel out. So we're going to do this and then rearrange terms. So equals 1/2. Better to write it like this. 1/2 gamma mu nu gamma mu gamma nu partial partial, then plus gamma nu gamma mu partials, and then plus 1/2 gamma mu gamma nu partial nu, and then minus gamma nu gamma mu nu. Okay. This is quite a long thing. Then minus plus, sorry, not minus, plus m squared, all of this times capital P. And this is right here. This is what we call the relationship for the anti-commutator. So we can actually pull out these partial mu, partial nus to the outside, and we can just say that this is the definition. This is the definition of 1/2 anti-commutator of gamma mu, gamma nu, and then you have the partial mu, partial nu here. And then similarly, you can do something over here, but this is called the commutator. So you get 1/2, the commutator bracket, partial mu, partial nu, plus m squared. All of that times C, the direct spinner. Okay, so we have this term now. Well, we know that for Clifford, what do you call it? Clifford algebras, the anti-commutator here is going to be 0, and this by definition gives you, or there was the Clifford algebra relationship that was given in one of the last videos. It was gamma mu gamma nu is equal to 2 eta mu nu, which means that this thing, because it's divided by 2, is just equal to eta mu nu. And then this is actually 0. So you can rewrite it as eta mu nu, partial nu, then plus m squared, and then psi. And then by the property, which is by the property of raising indices here, these nu's will cancel out. And so you get the last term, which is partial mu plus m squared c. And if you recall correctly, this is actually the Klein-Gordon equation. And so what this tells us is that if we have the Dirac equation, a Dirac spinor also satisfies the Klein-Gordon equation. So this is the Klein-Gordon equation. And more accurately, this tells us each component of C satisfies the Klein-Gordon equation. Right, because there are 4 components here, and this just means that for every component, the Klein-Gordon equation is satisfied. This means that there is a wave-like structure, of course, and so this is what motivates the form. This is what motivates the form C equal to E minus plus I k mu x mu times some spinor. This is what motivates this, is seeing that it satisfies the Klein-Gordon equation. So you get a wave-like component and then something that's left, or that's not affected by the wave. So let's actually plug this back into the Dirac equation. So if we have 0 equal to Dirac operator times psi, this is just I gamma mu partial mu of e to the, and we're just going to stick with the positives, or the minus here. We're not going to do plus or minus. C, and then minus m c, or I forgot to put this here, minus I k mu x mu c. And now we take the derivative of this portion, so we get a minus I and an I, so that's just negative I squared, so that's positive 1. So we just end up with gamma mu times k mu times e to the minus I k mu x mu c minus m c. Oh, I keep forgetting to write this term in, so let me put that back in. And because this is all equal to 0, we can divide out the wave-like structure, and we can just get gamma mu k mu c minus m c. Okay, and now that we've done this, this is actually the novel feature of the Dirac equation. I don't know why I kind of zoned out there for a second, but this is the um, novel feature of the Dirac equation, because the other feature of it was telling us that solutions are wave-like. We already knew that, so it's not new physics, but the new physics comes from this linear relationship right here that comes when you divide out the wave-like structure. So the easiest case to analyze of this, the easiest case to analyze, the easiest case to analyze, keep writing, analyze is the field's rest frame. Field's rest frame. And that is when this k mu here is just equal to k naught, and all the other components are 0, which means it's only moving in time. And so if we plug this into the dispersion relationship, if you recall k mu equals m squared, if we plug this into the dispersion relationship, the fact that k mu right now is only k naught, then we end up with k naught, which is equal to k naught squared, which is equal to m squared, which implies that k naught equals m. And this means that the wave-like structure, f plus or minus x mu, is equal to e minus plus I mt. And this is actually the form that we were working with in the last video. So if you recall, when we were talking about solutions in the last video, they were dealing with IMT. And so we were actually dealing with rest frames. Rest frames. Oh, there's this I didn't move over. There we go. So technically the drawings I gave here, which show oscillations going at 90, are technically incorrect. They wouldn't be going, they wouldn't look like this per se. So the best way to actually draw them would be actually if I just copy this, copy, paste it again. So we have this. Delete that. Delete that. Okay, so most accurate thing would be if we go from here to exactly twice the. Let me make it smaller so it's easier to see. To here to about twice that distance. And this would more clearly show it, where in its rest frame, it's oscillating back and forth, but the average position is actually straight like this. You do get that it does when it's when you move out of this rest frame, you do see it oscillate still, but it's not going to oscillate It's not going to look like this where they travel equal amounts. This is why the drawing was off last time. So this is why. So basically, the fact that the field has a rest frame at all means it has an effective mass. So to further analyze, to further analyze spinor structure, we return to the form C equals alpha beta, where alpha is a left-handed vial spinner and beta is a right-handed vial spinner. Or we look at this and then we look at we then come here and then we look at this relationship, see what the structure looks like. We get 0 equals gamma naught MC minus MC, which we can then divide by M. So we get gamma naught C minus C. And if this kind of looks like a projector, then you're onto something. That's a geometric, or it's an approach that's very, very not in this series. But let's expand this a little bit more. So this is a matrix, 2 by 2, 1 by 1 matrices, or identity matrices. Then we have alpha, beta, minus alpha, beta equals. Now when we perform this, we get only beta in the top, so beta, and we get alpha minus alpha, beta, which this is only true. This is only true if alpha equals beta. And so that's what this means, alpha equals beta. So this lets us define a basis of linearly independent solutions. So we can call the first one C1. We can say that it's the time-like or the wave-like component is just this. And then the C is going to be 0 or 1, 0, 1, 0, because alpha is equal to beta, so 1, 0, 1, 0. And C2 also is negative IMT. The other case for a linearly independent basis is 0, 1, 0, 1. So these are the two linearly independent solutions. And if now this was the case, where we used the minus IMT, where we had what you call it? We had minus IMT here. In the case that we are actually using in the case we use C is equal to F minus X mu C, which is again the positive, we get a different basis set. And basically we get that the negative beta, negative alpha minus alpha beta is equal to 0, which implies that alpha equals negative beta. Therefore, and then I'm just going to copy this actually. And have these as solutions, except they are positive I, and you get minus ones. So these are your two independent sets. And we saw these in the last video, but here's actually how they are, or how we came to them.